My name is Conor Dore, and I'm going to be presenting today research that's been carried out in the Dublin Institute of Technology in Bolton Street. And the research is on BIM for existing buildings, so not new proposed buildings, but actually modelling existing and historical buildings. The title is Laser Scan to As-Built BIM. I'm going to start off by just showing a short video, just showing an example of a case study that's been carried out as part of this research, where a street in Dublin, Henrietta Street, located very near DIT Bolton Street, has been recorded using laser scanning technology. And from this data, this laser scan point cloud, an as-built building information model has been created. As you can see, this is the BIM model on the right, and this on the left is the point cloud, which is obtained from laser scanning. It's a partially complete BIM model, so it's not fully complete, but it's just showing an example of the kind of models that can be created. And this model was created using some new techniques that are developed with this project, which I'll go through in this presentation. So basically, the project is on BIM for existing buildings, as-built BIM. And as-built BIM is a fairly new term that's now been used to describe BIM for existing buildings. So it includes both an as-built condition, so after a building is built, but also an as-is condition, so the current condition of a building. One definition of an as-built BIM is a building described with a BIM representation at the time of survey, which is important. And accurate as-built BIMs are needed for many applications in the construction industry, such as for managing buildings, renovations, retrofitting, conservation. And one important thing about as-built BIMs is that accurate survey data is required, as opposed to just design models where there can be discrepancies from what was actually built to what was designed. So survey data accurate survey data is crucial. And one very useful way for collecting this data is from laser scanning. It's become very popular for generating as-built BIMs. Laser scanning can acquire the data very quickly and can acquire very accurate data to produce your BIM models. There's 3 stages to a scan that I've broken it down to 3 stages for the scan to BIM process. The first is your data collection, so where you're actually collecting the survey data, whether it's laser scanning or traditional survey techniques. The second is a pre-processing stage, where you have to pre-process the survey data, such as point clouds, to generate products that can be used within BIM for the 3D modelling, which is the final stage. I think from my own experience that the 3D modelling stage within BIM is the longest stage of this process, the scan to BIM process, and that's what this presentation will focus on, the modelling within BIM. There's 2 main problems that I've outlined here with the whole scan to BIM process. The first is that there's very limited tools for modelling existing and historical buildings with BIM. So BIM is designed for modern new buildings, and there's very extensive libraries for modern buildings, but when it comes to existing and historical buildings, there's very limited parametric libraries that can be used. The second, another part of that is just limited tools for modelling the current condition of a building. So a lot of parametric library objects within BIM software are designed for the ideal condition, whereas in reality, existing and historical buildings, they can contain deformation, damages caused over time, which need to be modelled. The second major problem is that currently there's little or no automation in the as-built BIM process. So it's very much a manual process to generate your BIM models from survey data. And manual modelling of existing buildings from survey data, such as point clouds, it's a very time-consuming, tedious and labour-intensive task. And there's very promising research being carried out in other areas, such as computer vision relating to automated 3D modelling. But to date, these aren't being applied to the construction industry. So to give a background, one area of 3D modelling that's being developed in another completely different area in computer vision is procedural modelling. And this is generally used, it's an automated form of generating 3D geometries, and it's generally used for applications such as film or gaming, where large scenes where geometry for large scenes can be randomly generated. It uses rules and algorithms to generate the 3D content, as opposed to a person actually manually building it. However, recent research, these techniques have been applied to existing and historical buildings. And this is just an example of procedural modelling, where you can see it's computer-generated architecture. So instead of a person manually building the entire model, it's automatically generated from rules and from algorithms. So, but it's very similar principles to BIM in that, as you can see here in this particular model, the whole model is completely changing, and it's been changed by altering parameters and changing rules to build the geometry. So the advantage of these techniques to the construction industry and to BIM would be increasing the amount of automation. So it's more computer generated as opposed to purely manual. So my own research project and research that's been carried out in DIT involves developing similar techniques for BIM software. So to date, a semi-automatic method has been introduced for modelling building facades, but future work will be to try and extend this to complete buildings. So it's a more of a programming approach to 3D modelling. The techniques are being implemented within BIM software. So the first stage involved in this process was actually developing a library of new parametric building objects. And these are reusable parametric objects, so they can be reused again and again with different parameters. And these are specifically for existing and historical buildings. So these objects have been designed specifically at the moment for the ArchiCAD BIM software. So various objects for historical elements are being developed, as you can see here, and various small objects for classical style architecture are being developed and coded within the ArchiCAD BIM software. So very small and detailed objects that can be used again and again with varying parameters to speed up the modelling process. So this is a summary of the design process for this new library of objects, quite an extensive library of objects for historical buildings. These objects have been designed from historic pattern books and architectural information to get the original rules and proportions for these architectural elements. And then a grammar or a set of shapes are being used from this historic data and a set of rules to build the objects. So after the objects, using these objects, the next stage, stage 2, involved developing a plugin for the ArchiCAD BIM software to automatically combine these various library objects to generate building models. So again, with this plugin, historic and architectural knowledge is used as a basis to assist the reconstruction process, and a basic vocabulary of shapes are being used, and with a set of rules to automatically combine these shapes to build the geometry. So this is just showing a small clip to show you an example of what I mean. So it's using like a template for a building model, and by changing parameters you can automatically generate the required structure for your building. So you could change parameters for the number of stories, the number of horizontal tiles, the position of a door. So this is just a basic example of concept. And by altering these parameters, the geometry can be automatically generated. And the next stage then is altering or fine-tuning the geometry to fit the survey data. So these tools have been developed specifically for historical buildings with classical style architecture, but they can be used essentially on any type on other types of architecture as well. So I'm just going to show an example of the process of modelling a particular facade, number 3 in Henrietta Street in Dublin. So the first stage, the user takes 2 measurements from your survey data. In this case, orthographic imagery is used, but 3D point clouds or other survey data could be used as well. And these 2 measurements are used to provide an initial estimate to this facade elements. So it uses rules, proportions, classical rules to estimate the positions on a facade. Next then, parameters are edited to automatically generate the required structure for your facade. And finally, the automatically generated geometry is overlaid with survey data. In this case, a simple orthographic image is used, but it could be overlaid in 3D with a point cloud as well. And once it's generated, then the final stage is refining or fine-tuning the automatically generated geometry. So as you can see here, various methods for fast editing have been developed. So you can edit individual objects, or you can select groups of objects together. So you could select all the windows on a particular floor and say, I want to change the height of these windows together. So it provides very fast methods for editing. Alternatively, for more precise results, you can select a specific window and simply graphically edit the model. So simply clicking your window and moving it to match the survey data. So whereas in the past, if you were creating models from survey data, you might have to take a lot of measurements from your point cloud or from your survey data and type these in as parameters to your object. And with these tools, you can simply graphically modify your geometry to fit your survey data, which is a faster method of editing. So I know this is just a very basic facade with just the windows, but you can see how quickly, in less than 2 minutes, this basic facade was generated. Another major problem with modelling existing and historical buildings is that there's very limited tools for modelling deformation. So we're trying to develop more methods for modelling, non-uniform or irregular geometries. So such as like non-vertical walls, irregular objects caused by damage. So we're trying to develop methods for modelling this kinds of deformation. And to date, a simple basic framework has been implemented, but future work on this project will involve incorporating more complex architectural elements into the facade or parametric building, and also developing more techniques for modelling irregular objects or deformation. And also, further work is also going to be looking at extending these techniques not just from facades but to complete buildings for a more automated or procedural generation of geometry. And some of the benefits then that this automation would, first of all, accurate as-built BIMs are very important at the moment in the construction industry. And modelling is the longest stage of a scan to BIM project. There's very little automation currently within this process. So this research is trying to introduce a certain amount of automation to this current manual process, which will result in increased efficiency and reducing costs for such projects. So I'm going to finish up by just showing a few more screenshots from a case study of Henrietta Street. 10 scans were carried out to record the geometry on the street. And this is just a point cloud from the information gathered from the laser scanning. And this was then used to generate an as-built BIM model. And if you were to generate a model such as this using complete manual techniques, it would probably take weeks. But using the developed techniques, each facade was generated and refined to the survey data in a very short amount of time. And also new library objects that have been developed have been added to the model, such as you can see a direct door case just here. And again, once you have your model automatically generated, then you can use it to produce various 2D documentation automatically. And your normal products from the BIM, such as automatic 2D, 3D documentation, lists of objects, bills of quantities, for various applications, energy, structural, economic analysis. And some of the future work, which I already covered, involving more testing of the developed techniques and extending them from facades to complete buildings. So I'd like to thank you, everyone, for your attention, and happy to take any questions.